Yes. Okay. Good afternoon. Good afternoon. Okay. Hang on. Okay. 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 Hang on. Hang on. Yes, indeed. Good afternoon, Luna. Good afternoon, Daniel. Good afternoon, Mariam. Oh, 1 second. Good afternoon, Yorgelis. Good afternoon, Jenna. Good afternoon, Stephanie. Good afternoon, Darina. Good afternoon, Ashley. Oh, this is like the most consistent set of good afternoons ever. Okay. Great to see you all. We're gonna have like a class. That would be an interesting surprise. Let me wait. Oh, who else? Oh, good afternoon, Sam. Oh, more people. Okay, hold on. And hi, yes, hi. And good afternoon. Did I say Jennifer? Good afternoon, Jen, or maybe Jennifer's joining right now. Sorry. Hi, good afternoon. Oh, hello, Jennifer, I mean, sorry. And hi, Sam. And yeah, I didn't, and hello, Nikaya. And okay. Oh, and hello, Amarani. Yeah, funny you should ask direct chat person. I was just about to address that. Okay, so the fast answer is no, actually, but okay. So okay, so hello, everybody. Let me see if I can. Okay, we have much to do today, but yes, there is one question in the direct chat and on everybody's mind. And let me try to be fast about this. For good or for bad, well, for good or for bad, here is the deal. We will not be having a midterm. Maybe I should even put that in the chat, but that is a new information that is perhaps somewhat unusual or surprising information. The semester, we're all of a sudden, the semester started running away from me and my consciousness, and I was getting set to start announcing a midterm, and then I realized how close we are to final exams and how stressful that would be for everyone, I think. So we are not going to have a midterm at all, and that is a change. But let me tell you, in case, and hopefully that will make life better for many of you. Let me say a couple things about it, though, in case it might strike some of you as more stressful or more worrisome. Here's the deal. First of all, I have tons and tons of grading data on all of you. Still some things to wait. Well, that's what I'm going to, yeah, I'm going to explain right now. Well, let me wait. No, well, yeah, this is what I'm about to explain. I mean, good question in the direct chat. Here is the deal. We are just going to have a final exam. It is going to be a take-home exam. You're going to have a practice exam for like a practice document for it, that not just yet, but pretty soon you'll be given a practice document that looks very, very much like the final exam. You'll have time to do it and go over it, and we will have time in class and possibly lab, although I can't guarantee that, but in class, we will have time to address questions about the practice exam, for me to give some solutions to the practice exam, not all, but I will provide substantial solutions to things in the practice exam. Then the actual exam will strongly resemble the practice exam. In fact, in places where I don't give you solutions at all, it will be exactly the same as a practice exam. Like some places I won't give you solutions because that will be exactly what's on the final. Other places where I give you solutions, I might tweak things slightly for the final, like change numbers to protect the innocent or whatever. But so we'll do the old routine that we've done before for the final exam, in that you'll be very prepared for it. And the final exam will be take home, open, everything. You know, you can consult friends. You should consult friends. You can consult the interwebs. You should consult the interwebs. You can do it in stages. You know, you'll have like a week to do the take home final exam. You'll have all of, okay, wait. Well, so what I'm saying now, yes, but I'll tell you right now, I'll tell you right now, the final exam will be posted more or less. And in fact, if you could help me by telling me in a second in the chat, more or less, we're going to post the final exam like the day after the last class, up until whatever the last class is that is scheduled. So if someone wants to research that right now and put in the chat, that might help. But the last class or two, we will be going over solutions and questions to the practice exam. And then you'll have pretty much the entire final exam period to do the final exam. It will be due basically the last day of finals. So there won't, so if that, I can be more specific about that if anybody wants to put in the chat what the last day of classes are or and the official final exam period. But basically, you'll have the whole final exam period to do your final exam for this class, which I think actually usually means you'll probably have till like December 22nd or something like, or no, well, you better tell me, but whatever the last day of final exams is basically when your exam will be due here. But let me also add another thing. In case you're concerned about grades and things like that, first, I want you to know I have a lot more grading data on you than you might realize, because all of the game turns that you've done, all of the homeworks and everything that you've turned in, and I still have some to turn back, but all that stuff that you turned in, all those points are points that build on your average. And plus you have whatever you've done in lab counts. But so you're already going in with more of a grade and more of a good grade than you might realize. But when I give the practice exam, when I distribute the practice exam, I'm also going to say that there will be an optional part of it. There will be a part of it that you can opt to do for an extra grade if you're concerned about your grade, and if you don't want like everything hinging too much on your final exam. We will say that there'll be an optional part of the practice exam that you can do for a grade that can count as like a midterm grade if it will help you. I will tell you right now that if I grade it and it turns out it's like low, it's going to be lower than your final exam, or it's going to hurt your grade in some way, then I won't count it. But for an extra cushion, if you're concerned, because the one thing that, of course, by eliminating a midterm, which I'm doing, I'm eliminating the midterm out of concern for the calendar and concern for, the fact that we're already now about to be into the holidays and all of that. If you're concerned that by eliminating the midterm, I've eliminated a grade that might have helped you going into the final exam, then let me repeat that part of the practice exam, I will alert you when I distribute it, but you'll have a part that you can do for a grade, for like a retro midterm grade. And I will count it as such, as long as it helps your grade. And I won't if it doesn't. Okay. So in other words, you can have a midterm grade and a final grade if you need them. And if you think if you're too worried that too much is going to ride on your final grade. And again, I will count extra numbers to the extent that they will help your grade, and I won't if they won't. I don't want to get into all the details of this too, but if I will also say, like, if you end up tanking the final, but you do really well on that optional part, I'll put more weight on the optional part. In other words, believe me, just please believe me, especially if you have me for Physics 203, like, you and I are both equally interested in doing whatever we can to optimize your grade as fairly as possible. Like, I don't believe in cheating. I don't believe that you believe in cheating. So we're not going to make up a grade for you. I'm not going to gift people A's just like on a silver platter just for existing. But I will say that whatever you give me to work with, including all these game turn assignments, and you still can retroactively give me old assignments too, by the way, as long as it gets a little weird to start giving me tons and tons of game assignments. Like, some people are sort of doing that right now. I'm not really asking for that. The game assignments are meant to be indications of how you participated in class that day. And they're meant to be sort of moments of reflection and check-in on that day. So a day or two late on the game assignment's okay, but don't give me a ton of those now. But if there's old homeworks that you never did or whatever and the link is still open, you can do that. What I would really say is just try to stay with the material. And the minute I give you a practice exam, I think you should focus your attention on that and just on really being prepared for the final. And if you want doing any part of the practice exam that I say is worth optional points. Again, I don't I don't want you to be overly stressed about your grades. I want you just to remember one thing. I mean, you have to do the work. You'll have to take the final. You have to take it honestly, which means honestly write down things only that you have ultimately come to understand, right? So again, it means you can get whatever help you want to work through the final. You can, and please do, work with your colleagues, your friends, get help from the outside, blah, blah, blah. I will supply solutions and help in class. You can get, you're not being tested on what you already know. You're being tested so that you come to know it. So get whatever help you want. Then by the time you sit down to write out your exam, just make sure that you're only writing things that you understand. The more you actually understand something, the more you can and should write to demonstrate those details of understanding to me. The more colors you should use, the more pictures you should supply, blah, blah, blah. And when you don't understand something on the exam, and I don't mean to get into all this right now, but when you don't understand something on the final exam, also the more you can delineate and specify exactly what you do and don't understand, the better. Just the more you can honestly communicate your personal comprehension of this material, that's what we're ultimately looking for on the final exam, like authenticity, not accuracy as such. I mean, accuracy is good too, but anyway, I think some of you have done this before with me and you sort of know what I'm saying, hopefully, but what I'm really trying to say right now is no, we're going to skip the midterm because time is running out. And I think it'd be a lot of stress right now for a lot of people that then would just come right up against the final exam. And it would, by the time I would grade it, it would be the final, it wouldn't even help you. I wouldn't be able to get it back fast enough to really help you with the final exam. So, right, we're going to do one big final exam with some of the preparation for it being available for optional grade and optional points to the extent that those points help you. And what I was just saying again, no problem. Oh, and thank you for asking. No, and thank you for saying thank you. No, good. I'm glad. I meant to bring this up last. No, I'm glad we're addressing this now. Let me just remind you too, and there's still material to do, right? I mean, I want to get back to material, and I do want to get to certain punchlines in this course. Like I do want to continue to be able to teach you until the last minute. Then that's the other reason. I just don't want to get all bogged down in midterm, because then we're just like, we'll go into the black hole of academics instead of intellectual material. But the other thing, just to remind you, and I hope that most of you, I hope that if you had me for 203, you found the following to be true. And if you did, maybe assure other people who didn't have me for 203, whatever. I'm not promising you all an A. I can't do that because we're not done yet. And because you have to earn the A, right? It isn't an A if I just like give it to you in advance. So I'm not here to promise that necessarily you all get A's, but I am here to promise that I'm just as happy as you are if you all do get A's and earn them. Like, I want to remind you that I don't have a distribution curve in mind. I've had some professors who did. I've had professors in my life who very openly had a philosophy that said only a certain number of A's could be recorded in a class. I actually think that's a completely coherent philosophy. I don't think there's anything, I think it makes sense, but it's not my philosophy. And I think that knowing the philosophy of the professor when you're going into an exam or going into the grading portion of the semester, like, actually affects how you behave. So I want you all to know I'm perfectly happy with you all getting A's as long as they're honest A's. Like, and I'm actually just as interested in that as you are. So just know whatever happens from here on in, whatever's hard about the material or whatever's hard about the course, hopefully is just what's hard about the material. And just know that you're not in a competition against me and I'm not in a competition against you. We are together in a competition against the challenges that are intrinsic to physics mastery. Okay, like honestly, and I'm not grading you on being physicists because I don't know what grade I would receive if I were being graded on being a physicist. I mean, it depends who you put me next to. If you put me next to my heroes, Galileo and Einstein, I totally would not get an A, right? But what we're being graded on here is as physics students, as physics scholars, we are being graded on how intensely, how authentically, how responsibly did we engage with the physics material and how intensely and successfully did we progress through the material that was presented to us in this academic setting, right? And that's why I believe it's totally conceivable that all of you, and in fact, my sense, I'm looking at the boxes, the squares right now, like I know most of you. I feel like most of you have stepped up and found a way to make yourself known to me, whether it's in private chat or private homework submissions or being early every single time or like whatever. And so if I'm here to grade you on whether you've engaged with this physics material and done your best to advance through it and stretch your mind and put more in there of physics, like that's what I'm trying to grade you on. And I see room for everybody to get an A, and hopefully everybody will. I mean, hopefully, and again, just enough people just automatically won't, that it, unfortunately, like, and those people are probably not here right now and probably are often not here, if you know what I'm saying. So anyway, so I want you to have as much intensity and excitement going into the final as possible, but as little stress as possible. I made the mistake for way too much of my life thinking that hard work automatically means stress. And if I'm not stressing, then I must not be working. That is not true. There's a way to work that is intense and honorable, that is not necessarily stress. Stress is just inefficient work. Okay, cool. All right, and I'm talking too much, but cool. Okay. Cool. All right. Thank you both for thank you for the direct chat questions. And again, and to Miriam's question to everybody, which is totally legit about dates. I'm being a little sketchy about dates right now, just because like I'm not literally looking at a calendar and I don't want to say something wrong. But if at any point in this class, but I will get back to you on that. What I'm basically am saying is more or less, but the day after our last class, which I don't know, is that December 13th, something like that? I just don't want to say something wrong and be quoted on. And once I get this clarified, I'll put it in the Google Classroom. But essentially the day after our last class, I will post the final exam, okay, in Google Classroom, like, as though it were an assignment. And essentially like the second to last or last day of finals, something like that, is when it'll be due back. I'm being a little bit vague to protect myself a little, because I know if I get all the final exams from every single course on the very last day, I might have trouble getting you grades in time and stuff, but that's basically the idea. And if anybody puts in the chat, what, like the last day of class, oh, there we go. Okay, thanks. Although, okay, I'll try. Thank you, Sam. That might be, okay. I was sort of hoping you, okay. All right. I'll look at that right now. Okay, hold on. I'll do this. Let me see if I can figure this out fast. I will. I don't mean to stutter, but okay. No, this is, okay. I think, okay. So thank you, Sam, twice. I mean, okay. Okay. Whoa. Oh, okay. Last day of, oh my God. Okay. No, thank you, Sam. All right. So I'm going to say this. I'm not going to write. I'm going to say this now. Then I will try to put this in the Google Classroom, but just in case I'm so 6th, 7, 8, 9. So basically like the 10th or so, by December 10th, good heavens, I will post the final exam, and then your exam will be due, let's say, just to be careful. What do I say? Like your final exam will be due like the 20th. Okay. So again, I'm not writing this down sort of on purpose, but you can write it down. I'm saying because the last day weekday class is the 13th. Why am I having a problem with this? 6, 7, 8, 9. Yeah, your final exam will be posted around the 10th, maybe a little bit later, and it'll be due around the 20th. This is all of December. Okay, basically like that. And I'm glad you showed, which means like a week before by December 3rd, we should be talking about your practice exam and all of that. Like we'll have like a week, like 2 classes to deal with your practice exam. Okay, that's essentially the story. Thank you, Sam, I'm gonna actually, okay. Sorry. Okay, hopefully that's somewhat clarifying, and I'm trying to, okay. Sorry. Okay. So hopefully that's somewhat clear. So we'll talk more about that next class too. But now, if that's cool, I'm going to get back to material. What? Okay. Okay. Oh, okay. Actually, as long as we're doing, can I just get in the chat? Can you, I know that wasn't perfectly precise, but if that was basically clarifying, could you just write like, yeah, or got it or something in the chat? Okay, cool. Thank you. That's 1, 2. Okay, great. Thank you. Awesome. Okay, great. I mean, I'm not expecting everybody to do that, but I'm going to take that as, all right, I appreciate it. And I appreciate the opportunity to clarify that. Yeah, before that, right. Okay, thank you, Daniel. Thank you, Stephanie. Thank you, Sam. Thank you, Jenna. Thank you, Miriam. Thank you, Amarani. Thank you, Luna. Thank you, Dorina. Okay. Oh, hello, Dorina. I didn't even say. Okay, great. Okay. And hello, Yorgelis. And okay. And thank you, Jennifer. Okay. So I'm going to get back to material now. And again, we're never going to get to every, I'm never going to get to say everything to you that I would like in the subject of physics. That's too bad for me, but I want to say as much. Oh, but to confirm, yeah, to confirm, you will. Yes, I will put these details in Google. I mean, that's fair. Good question, Stephanie. I will. I mean, I don't know about like right now, but I will. Once it's totally clarified in my head, I'll put it in Google just so it's clear. Yes. Yeah, good. Thank you. Yes, cool. Okay. Okay, so let me just switch. So now I want to get back to the material, and the material, and again, I'm going to try to be a little bit more big picture with the rest of the semester also, so you can see, I mean, there have been, a big theme of this whole course is unthingy motion, like I was mentioning last week, and when I say unthingy, of course, that's a non-technical term. What I really mean is immaterial motion. I mean, motion from here to there that's real, that's observable, measurable, analyzable, predictable, scientifically verifiable, but immaterial, right? Motion that goes from here to there, for which there is no discrete, individual, particular, identifiable, countable, massive entity that actually goes from here to there. Best, in some ways, the most concrete example we have of such an intangible idea is sound. That's one of the reasons we've sort of did so much to build up. We did all this harmonic oscillation stuff, a lot of math, a lot of abstract math, deal with harmonic oscillation, so that we could put a bunch of harmonic oscillators together into a big collection, right? And create this thing called a wave pulse, a wave propagation. And then we focused on an example of a sound wave pulse, and focused on the example of a sound wave pulse undergoing a Doppler effect. Because in some way, I mean, that's like really mostly what we've done in this course so far, right? And I don't know if that seems like a lot or a little to you, but to me, what that is a story of, that's my best attempt to give you a story that's as concrete as possible, and as specific and as numerical and as logical as possible about something that is super familiar to all of us and super real to all of us, but super immaterial: sound. Okay. And again, by the way, the reason we spend all the time on the Doppler effect of sound is because the Doppler effect is an example, like sound is already an example of wave motion. And I cannot emphasize enough, like if we were to have to end the course right now, like I still hope that I've given you something, or I want to feel that I've given you something by really analyzing sound as a physicist, because sound is an example of something we all believe in, we all like use and experience all the time. It's like such a real part of our real world. And it's so scientifically analyzable, right? I mean, we can talk about its speed, we can predict when it's going to be over here, when it's over there, we control it, we play music with it, we do all these, sound is so accessible to us, and so in some ways predictable and controllable by us, but it's so immaterial, right? Like sound entities don't exist. There's no such thing as a sound on, so to speak. Like there's no such thing as a particle of sound. Now, I don't want to say that, except I do, because that's a big takeaway of this course, that we could be so real about something that is so not tangible or not material. And the Doppler effect piece is supposed to be an example of something that sound does, or that happens to sound, that only happens to sound because of its wave nature. The Doppler effect is almost like a piece of, if you like, mathematical evidence or mathematical demonstration of something that literally could not be explained if there were such thing as little sound particles going from my mouth to your ear. Like not just the idea of a Doppler effect, but the particularities of it. And I'm not trying to go back down that road now, but just to get, so anyway, that's all a long way of saying the focus of this course is the principles and practices of physics, the study of motion as it applies to immaterial motions. Like that's what distinguishes physics 204 from physics 203. And it's not a coincidence that in some ways the math of physics 204 is more sophisticated, I think, or more abstract or more advanced than the math of physics 203, because we're dealing with the same laws of physics and the same tendencies of physics, but we're dealing with entities now that are more abstract and more sophisticated than in physics 203. Okay. All that said, whatever time we have left in this course, I want to deal with another example of an immaterial manifestation of motion, or an immaterial player in the act of motion. And the name and so what we're dealing with now in the course is what you might call action at addition. Sorry, I just lost my. We're dealing with now action at a distance. I'm ultimately trying to present to you and analyze to you this second equation on this sheet that has to do with the electrostatic interaction. And I know we started that last week. We started discussing the electrostatic force between 2 point charges. Right, the electrostatic force that that exists between a proton and an electron, or a proton and a proton, or an electron and electron, and we're starting to deal with the math of that. And what I'm saying to everybody is the mathematics of the electrostatic force, the electrostatic interaction, bear an incredible similarity to the mathematics of the gravitational interaction, the gravitational force. They're both inverse R squared forces. And interestingly, they're both forces that occur at a distance, meaning through empty space, meaning the way the sun pulls on the earth, the way the proton pulls on an electron, both of them don't require any physical contact. They don't require any physical action. Like the sun doesn't have to reach out and touch the earth in any way. The sun doesn't have to be in material contact with the earth for it to pull it. And furthermore, there could even be stuff between the sun and the earth, and that wouldn't stop the sun's ability from pulling on the earth. This is the same idea as protons to electrons, or protons to other protons. Some people call these interactions fundamental. Some people call them action at a distance. It's the same idea either way. And some people notice that both of these actions at a distance have the same mathematics underlying them. So what I want to probe this action at a distance business for a minute. Again, it's an example of something happening in the material world that seems to be immaterial. When I say it's immaterial, I mean, pardon me for a second. Yeah, I mean, like, let's think about this for a second. If we all believe that the sun, we believe that we're all being pulled down to the center of the earth all the time by this thing that we call gravity. And we believe it because we're so used to it, because we see it happen every single day. Kind of like sound. It's so familiar to us that when you hold something, it just drops. It automatically just seems to be automatically pulled towards the center of the earth. We're so used to it that we're used to it. right? But what is it that we're believing? Whenever we use the word gravity, we're believing that somehow the center of the earth yanks on any object that we're holding, yanks on it through empty space. Like it's just some pull that seems to just exist between the two. And we've come to believe, because we've been told many times, we've come in the 20th century, 21st century, we believe something that we have believed since the 18th century, which is that this is not just some special property of the earth pulling on objects. It seems to be a property of the universe, that all objects pull on all objects through empty space in this way. And that, for example, the sun pulls on the earth by virtue of the same phenomenon. Now, I want to stop and sort of examine for a minute how weird that idea really is. I mean, we're very used to it, so it's not weird in that sense. But we've gotten used to something that, if we really think about for too long, is a little bit bothersome. If the sun actually pulls on the earth without touching it at all, right? Which we seem to believe, or we've believed since Newton. If the sun can pull on the earth without touching it at all, and more to the point, if we believe the equations that I gave you last week, and that by the way, I noticed that the equations on the front sheet here sort of look like what I gave you last week, but they sort of, the top equation might look like it's missing an M, and the bottom equation might look like it's missing a Q. And if you've noticed that, or if that's confusing you, good observation. Like my ultimate goal today is to explain why I've dropped one of the M's and one of the Q's from the equation, and I'm going to get to that. But even just holding that thought aside for the moment, if you just look at the form of the equation and notice like that there's an R squared in the denominator in both cases, and that there's stuff in the numerator, what those equations suggest is that the farther away the sun is from the earth, the less the sun pulls on the earth, right? And the closer the two are, the harder the sun pulls on the earth. And same thing with protons and electrons. Now, think about that for a minute. That means, if we believe that equation, if we believe it, it means that the sun is sitting here and pulling on the earth with a certain number of newtons, like we sort of, plugged in and calculated last week. The sun has a certain mass, we plug that in. The earth has a certain mass, we plug that in. There's a certain distance between the two of them. We square that and plug it into the denominator. We take the whole package of numbers and we multiply it by the gravitational constant, 6.67 times 10 to the negative 11 Newton meter squared times divided by kilogram squared. And so then all the units cancel out, we're left with newtons, and we have this force that the sun is pulling on the earth with. Like, if we believe this equation, and I'm not saying don't believe it, but I am saying let's think about it heavily for a second. According to this equation, then, the sun reaches out, pulls on the earth through empty space, starts yanking on the earth. And if all other things are equal, like if there's nothing else going on in the universe or nothing else significant going on, then the earth starts getting pulled in towards the sun. F net equals ma, the earth presumably would start accelerating in towards the sun, okay? And this does happen. The earth gets accelerated towards the sun, depending on whether it happens to have any velocity at that moment or not, and depending on what direction its velocity vector might be pointing, the earth may well start moving in closer to the sun now because it's accelerating towards the sun, because it's being pulled toward the sun, right? And sometimes this does happen. I mean, you may know that at different points in our elliptical orbit around the sun, sometimes we're closer to the sun and sometimes we're farther, right? So just imagine this one moment or this one set of moments where the sun is pulling on the earth from this gravitational force. The force is the net, let's assume, is the dominant force on the earth. F net equals ma, so the earth starts accelerating in towards the sun, let's assume, right? Well, now the earth is closer to the sun, right? I mean, if it just got pulled in, it's now closer to the sun. Well, according to this equation now, if it's closer to the sun now, the R in the denominator is smaller. So now, according to this equation, the force that the sun is exerting on the earth should now be bigger, right? And in fact, if the earth keeps being pulled toward the sun, this will keep happening. That is, every moment that the sun pulls on the earth through empty space with this gravitational interaction, every time it does that, it alters the location of the earth relative to the sun. And every time the location of the earth is altered relative to the sun, the force generated by the sun, according to this, alters in response alters accordingly, right? And by the way, if that's too abstract to think about or too weird, in a way, just take a much simpler example. If a stone is falling toward the earth because the earth is pulling on the stone, according to this, as the stone falls toward earth, every meter that it gets closer to earth, the R in the denominator is smaller. So the force on that stone should be greater. And where am I going with this? I'm going here. I'm going to ask, what? Wait, what? That means if that's true, if the sun adjusts its pull on the earth every moment that the earth moves and finds itself in a different location relative to the sun, doesn't that very vividly express the fact that somehow we're believing that somehow the information of the earth's location is getting to the sun? In other words, how does the sun adjust its pull on the earth? If the sun's pull on the earth is dependent on the earth's location, let me say that more clearly. If the magnitude of the sun's pull is dependent on the magnitude of the earth's displacement from the sun, that means that every time the earth changes its displacement from the sun, as for example, it would in response to a pull from the sun, then that means every time that displacement is changed, somehow the new information, the updated information, the new coordinates, if you like, of the Earth's new position somehow travel to the sun and get to the sun and prompt a readjustment of the pull being exerted by the sun. Right? I mean, there's no way around it. If we believe that the extent to which the sun is pulling on the earth depends on where the earth is, that's got to mean that at some level, the sun knows where the earth is. And I don't mean knows consciously, of course. I'm not trying to be ridiculous. I'm just saying the statement, even without trying to be ridiculous, is somewhat ridiculous. I don't mean the sun consciously knows where the earth is, but I just mean that somehow the information of the earth's whereabouts must be accessible to the sun in such a direct and real and concrete way that every time those whereabouts change, the sun's system has to change accordingly, and the sun's pull changes. That means we believe by the way, this all also applies to the Earth's mass, right? I mean, if the equation is right, the equation is saying that the sun pulls on the earth in a way that literally is determined by how big the earth is and where the earth is. And if either of those facts change, the pull changes. That means that those facts have to be somehow getting to the sun. The information of the earth's properties have to be getting to the sun if indeed the sun is pulling on the earth in a manner and magnitude that precisely depends on those properties. And the whole thing must be true and vice versa as well, right? The earth has to know how big the sun is and where it is if the earth's pull on it actually depends on those factors, right? That's kind of crazy. Like I don't mean to be getting excited, but I am. Every time I think about this, my mind, and I'm not trying to trick you. I mean, there is more to be said about this. There is resolution in a way, but whatever the resolution is that I say, whatever the answer to this question, I want you to know that the question never really goes away. Somehow we believe, if we believe in fundamental forces at all, if we believe that gravity acts through empty space, and therefore, if we believe that the Coulomb interaction, the electrostatic interaction between protons and electrons, which we believe is just like the gravitational interaction between masses, if we believe in these fundamental interactions, if we believe in action at a distance, we are somehow believing that numbers, that numerical values, that information travels through empty space from one object to another. Period. That information travels through. I mean, this is what I mean by an immaterial motion. Like waves were an example of an immaterial motion, but here's another one. Like action at a distance is, you might think of action at a distance like not as a motion. You might just think, well, we're just pulling through empty space. Why is that like such a big deal? We're just pulling through empty space. But what I'm saying is if the pulls through empty space or the pushes are actually dependent on numbers, then we're actually believing numbers are flying through space at some level, not numerals. I'm not being like Sesame Street. I mean, I love Sesame Street, but I'm not saying that I believe that like a plastic like number 2 is like flying through, but I am, right? So I'm not saying that, but I'm saying something immaterial is going through space. What immaterial? Information. Just like when I shout at you, somehow sound is going to your ear without anything going to your ear. I'm saying when the sun pulls on the earth, or when a proton pulls on an electron, if we believe it works this way mathematically, we are believing somehow that the earth is sending information of its properties, sending its mass and its location to the earth somehow for that to happen. And let me add one more thing. Once you believe that at all, and I'm not saying I know how, I sort of do, but not really. And I'm not saying that you should be able to picture that. I'm not sure that I can picture it. But I'm saying there's got to be we've got to sort of buy into that somehow if we're buying into these equations. Make matters a little bit crazier. If you believe this at all, and by the way, don't even try to believe it. Just try to, I don't even want you to like believe anything necessarily, but I want you to at least sort of like see the reasoning that I'm saying. Just see why X sort of implies Y, whether that just means you want to reject X. Oops, someone's here, sorry. Maybe all this means you want to reject the equations. I don't know. But these are the implications of the equations. Let me go one step further and say, if you believe these kind of equations, or the equations I gave you last week, if you believe that for the sun to pull on the earth, the information of Earth's size, like mass and position must somehow be sent to the sun, then the reason I made this whole long example of how every time the earth is pulled, it moves a little bit, and then the pull must be adjusted, and then it gets pulled more, and then it moves more, and then the pull must be adjusted again. What I'm trying to get at with all of that is to say, not like that this all must happen in time somehow. Like what this raises the question is, if we believe that the information describing the earth is somehow accessible to the sun, then it raises the question, does the information of the earth literally travel to the sun? Like you might say, well, I don't think it travels there. I don't think that's a motion, Yavor, but I'm like, okay, the sun knows somehow how big the earth is and where it is, but it's not because that information has to go on a journey to the sun. It's just automatically there at the sun, you might say. In other words, or you might not. Some of you might be picturing that if you accept at all the premise that I'm saying that somehow these equations mean that information describing Earth must be accessible to the sun, or information describing any random electron must be accessible to any other random proton. And also, by the way, if you're following me, you realize that I'm just looking at 2 objects at a time. But if what I'm saying is true, it's true of all objects at all time, right? Like, if this is true, that the sun needs to know how big the earth is and where the earth is in order to pull on it, well, it's also true that the sun needs to know Mercury, Mars, like everything. So everything apparently knows where everything else is at all. And what I'm saying then is you got 2 choices. Either we believe that the information of the earth automatically is just at the sun, or we believe that the information describing the earth travels to the sun. In other words, we have 2 choices. Either the information describing Earth takes a finite amount of time to get to the sun, or it doesn't take a finite amount of time, like it gets there in 0 time. In other words, either the information describing the Earth travels at a finite speed to the sun, or it travels at an infinite speed to the sun. Those are the only 2 options, like logically. It either is or it isn't, like whatever, right? And I'm here to say both of those options are deeply disturbing, deeply disturbing. Like if the information of the earth takes time to travel to the sun, if it travels at a finite speed, well, first of all, what speed? Second of all, if it's traveling at any finite speed at all, then that means that every time the earth moves, every time the sun pulls on the earth, it moves, and then it means there's a little delay before that new information gets to the sun. So it means that every time the earth moves, there's a little delay before the new information gets to the sun, and there's a little delay before the new force is like calculated and adjusted. And it means that as we watch the Earth get closer and closer to the sun, or as we watch something falling to Earth and getting closer and closer, even though it looks like a smooth movie, if actually we believe in this finite speed idea, then arguably it's not really a smooth movie. It's like a strobe light, like a disco, like a stop action kind of thing, because there's actually a gap between every new situation, a gap between the new situation and the sun finding out about the new situation. Or, and that's weird, like that's just really weird. I'm not saying that's wrong. I'm just saying, oh my God, I didn't think life was like that. Or the other option is, no. There's no delay. Just whatever the Earth is, like the sun just knows that, just period. It's just like already, the information's already there. But that's bizarre, because then that means when the Earth gets closer, now that information was already there at the sun. Like what, we don't even have to wait for the Earth to move for the sun to know where the Earth is. Like the Earth moves and instantaneously the sun knows it. That means that every bit of information about every particle in the universe is immediately everywhere. And then that means there's no different, like, then it doesn't matter how far away the sun is or anything is, everything is communicating with everything equally, like, in other words, if the information travels from the Earth to the sun at an infinite speed in no time at all, that means that the distance between the two doesn't matter at all. And that means there's no reason for things that are much farther away to be just as affected by each other as things that are really close. That seems really weird too. Am I saying that's wrong? No, I'm not. I'm just saying that this whole idea of action at a distance, I'm saying that action at a distance, which I do believe in, sort of, the idea of the gravitational force, the idea of the electrostatic force, which is really the focus for the rest of this class, the electrostatic force, if we really believe it's happening through space, through empty space, that's a really weird idea. And it is so weird. Let me get concrete now. It is so weird that you might notice I put something in your Google Classroom just this morning, just like in the material. It's not like an assignment or anything. It's just like a text excerpt that I'm going to share the screen about. I'm going to put on the screen right now. I want to show you that when Newton first published his idea of universal gravitation, GMM over R squared, when he first published that, a letter was written to one of Newton's heroes. Newton had, I mean, everybody has their intellectual mentors, even if for some of us, our intellectual mentor is Newton. Newton had his intellectual mentor as well. One of his intellectual mentors was a man named Sir Richard Bentley, who was like a don at Cambridge. I mean, in other words, a major professor, major academic, whose opinions on all matters and knowledge of all matters, Newton like really, really respected. And when Newton's theory of gravitation came out, a letter was written to Sir Richard Bentley that strongly objected to Newton's gravitational theory, strongly objected to this idea of action at a distance. And its objection was pivoting on the kinds of things I'm trying to say right now. In other words, I'm not just trying to give any of you a hard time. I'm trying to say that the idea of action at a distance is so controversial and so tricky that even when it came out, when it was published by Newton, there were major thinkers who had major reasonable objections to this idea that information could propagate through empty space. And one of those objections is really worth taking seriously. I'm going to show you. I mean, again, I put it in your Google Classroom so you can keep it forever, but let me show you right now. Yeah, hold on. Right, so I think, yes, okay. So there was an early critic, like I'm saying, there's this critic, and we're going to figure out who that critic was in a moment. I'm intentionally not mentioning yet. You've heard of him, but I'm saying who you might not have heard of was Sir Richard Bentley. So this critic writes to Sir Richard Bentley, writes a long letter objecting to Newton's gravitation. And this is Newton, right? Like Newton's like the man. I mean, Newton's no dummy. I mean, obviously we are more aware of him now than people were during his day, but they were pretty aware of him during his day. And so this critic writes to Sir Richard Bentley. Hopefully, yeah, you could see on the screen. He writes, among other things, again, this is excerpted, but these are the exact words, or at least the exact English translations of the word. And actually, it was written in English, I believe. But it might have been written in Latin. But anyway, it is inconceivable that inanimate brute matter should, without mediation of something else which is not matter, operate on and affect other matter without mutual contact. That gravity should be innate, inherent, and essential to matter. And by the way, anywhere you see the word gravity here, you can substitute the word electrostatics as well. Like electrostatics doesn't get discovered for another like 150 years, but everything we're saying about, so this is our earliest glimpses at action at a distance, but anything we believe about gravity, we now believe about electrostatics and vice versa. And it's all, this, anyway, that gravity should be innate, inherent, and essential to matter so that one body may act upon another at a distance through vacuum without the mediation of anything else by and through which their action may be conveyed from one another is to me, now check this out. This is what this guy is saying. He's saying it about Newton's work, and he's writing it to Sir Richard Bentley, who's this intellectual giant of the time, this scholar that our great heroes worship as the scholar of scholars. This guy is writing that gravity should be innate, inherent, and essential to matter is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Okay, so so this is a letter of critique to Richard Bentley, Cambridge, 1693. Again, Newton was born in 1642 and he dies in 1727. So this is, this is that a severely productive period of his life. Just look for one more time, if I still have your attention, just look at this language is so incredibly strong. I mean, the gravity should be innate, inherent, and essential to matter is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Literally, he's saying, I mean, and again, this is where I kind of wish we were live in a room together so I could just see your, like, do you understand? I mean, I think you understand when we say who has in philosophical matters a competent faculty of thinking. He doesn't mean faculty like, he means faculty like skill, like tool, like ability, capacity. So he's saying any man who has the slightest freaking clue in thinking could never fall for such a dumb, absurd idea as this. And what's the idea? The idea that he's saying is so absurd is that gravity could possibly take place through empty space. Okay. And one of the reasons this guy is so objecting to that is the stuff I was trying to say earlier in the class, that if you believe that, I mean, remember, he's not just objecting just to like the rough sort of speculation that there's this thing called gravity. I mean, he's objecting to the equation, the whole package, the idea that every mass in the universe is pulling on every other mass with a force measured in newtons that is determined by the two masses measured in kilograms divided by the square of their distance of separation measured in meters, right? Like, and he's saying, like, how could that precise numerical quantity get from one object to another through empty space without anything passing it along, without any medium to propagate that information, so to speak, right? Now, what I'm going to ask you, so hopefully you see, so I'm not telling you don't believe in gravity. I'm telling you that, oh, there's things in the chat. I'm sorry, hold on. Okay, I'm glad. All right, at least one person in the room is totally with me. Yes, okay, this person is calling Newton a dum-dum. That is right. Yes, and that is sort of savage in retrospect. Now, here's the thing. I'm glad I have at least one, and I'm sure I have other people's attention too. I'm not trying to, and I'm not trying to confuse you. I am obviously sort of trying to excite you. I'm trying to say that there's something deeply disturbing about the notion of gravity, something that we've got to do something with in order to make it like work in our stomachs. And when I say we, I mean any of us, the people that were first considering gravity and we today. Now, before we go on, and there is some way of resolving this. There are things in the way the rest of the course is an attempt to resolve this like feature of gravity, this curious feature of gravity as we seem to believe in it. But I'm going to ask you guys, I think this is worth, we've got 20 minutes. I'm going to tell you right now, you'll notice I'm telling you that this is an objection to Newton. I'm going to go back to the other thing too. And I'm telling you, Sorry, I'm just going to share the screen. Okay, I'm telling you that what you just read, what I just read to you, and again, it's in your Google Classroom if you ever want to like refer back to it. It's an objection to Newton. It's calling Newton a dum-dum. I'm also telling you that it was in a letter that was saved and was written to a scholar of the day named Sir Richard Bentley. I don't necessarily expect that anybody's heard of Sir Richard Bentley, but I'm also going to tell you now that the person that wrote that letter is someone you've heard of. I intentionally didn't put that thing on the piece of paper. The person that wrote this objection is a great physicist, was a great physicist, with whom you are familiar. Maybe not deeply familiar, but you do know of this physicist. This guy that's objecting to Newton is no slouch either. And it's actually a worthwhile exercise to spend like a minute and a half even trying to guess or determine who he was or who she was, but it wasn't a she, to be honest. I mean, it's the late 1600s. It was a he. Is it possible for any of you, first of all, can anybody just put in the chat if you're still with me, if you're still sort of hearing me at all, if you're still getting what I'm basically saying, just like I just want to make sure you could just put in the chat like, yeah, or yeah, great, thank you, awesome. Oh, that's so fast. I love this class. Thank you. Okay, awesome. Oh, it's so many of you too. Great. Okay. So thank you, Stephanie. Thank you, Amarani. Thank you, Mariam. Thank you, Daniel. Thank you, Ashley. And thank you, Sam. So that said, does anybody, and you don't have to, but for points or whatever, I'm going to ask you to spend a minute and a half, and don't Google it because it'll kind of ruin, but just guess. I'm telling you, you know the physicist that objected to Newton. Yep. And did you actually know that, or did you just figure that out? Oh, wow. Okay. And I don't know if anybody else is, wait, this semester or last semester, right? Or, okay. All right. So listen, everybody, I don't know if you caught that or not, or if you already knew that from Walters, but yeah. Okay. And so I'm sorry I'm spending so much time on this. If you've already all, and actually maybe you guys should tell me in the chat if you've already all seen all this already. I do kind of apologize, but yeah, what Sam is saying is true. And also, you can tell, look, and I'm sorry if I wasted your time if you already all knew this, but you can also tell, I tell this story like every single semester of my life for like 27 years, and I never get sick of it because it continues to blow my mind that the person that wrote that letter, this is what Sam is saying in case it's not clear, the person that wrote that letter that is calling Newton a dum-dum, that's objecting to Newton, is freaking Newton. I mean, and maybe just tell me in the chat if you already knew that, you guys. Yeah. Okay. Cool. And can anybody else, just so I know who I'm talking to or what? No, that's great, Sam. And Walters will be so thrilled that Sam at least remembers this, that it made an impression. Can anybody else just tell me honestly? Have you already? Oh, did not know that. Okay. So listen. I mean, no, and it does bear repeating. Like the point is that Newton wrote that letter to Richard Bentley, and it got saved and it got published. Newton, and he wasn't kidding. He was not kidding. Newton he did pretty much go insane by the end of his life. And what he was really saying in that letter was, this shit makes no sense. Like, this is so dumb. And this is so crazy. This cannot be right. He specifically could not reconcile the stuff I was saying at the beginning of, like, is his problem. Like, his point was, how could the information get there? Does it get there in no time, or does it get there in some amount of time? He could not reconcile it. Either option made no sense to Newton. It did not jive with his intuition. It did not jive with his experience. And he actually did, by the end of his life, the best idea that he could come up with was that the information must get there instantaneously, which makes, in fact, made so little sense to Newton that, in fact, it's not what we believe anymore. We don't. We believe that the information does get there in a finite amount of time, that the information of Earth's mass and Earth's position does travel toward the sun at a finite speed and does involve a time delay and does take time to get there. That's what we now believe. Newton did not believe that. Newton went insane over this stuff. And you might, in fact, ask, wait, but if he didn't believe it, like, why did he publish it? Like, what? I mean, is he like lying to himself or what? Well, this is one of the great This is the period in history where science breaks off from philosophy, or more specific, well, yeah, where, I mean, science used to be called natural philosophy. Everything was a philosophy. There was ethical philosophy, there was legal philosophy, there was theistic philosophy, social philosophy, and natural philosophy. All philosophy meant thinking about stuff, literally love of wisdom. Natural philosophy was applying our love of wisdom, our love of thinking to the natural world. And it was all just part of thinking. I mean, certainly in Aristotle's day, Plato's day, thinking was thinking, whether you were thinking about nature and natural laws of motion, or you were thinking about how governments should work. Political philosophy would be another example. But here, with Galileo and Newton, and with the advent of the controlled experiment, what Galileo and Newton are among the first people really to at least publish and say is, we now have a method for designing the collection of data. We now have methods for collecting information from space and time through our 5 bodily senses, getting that information into our minds and our brain, and reproducing that method for getting that information so that other people with other brains can do the same thing and get the same information. And that information is called data, and that method is called experiment, right? And what we're saying now, as of Galileo and Newton, is what we trust is reproducible methods for obtaining physical data. What we trust above all is data that comes in through our 5 senses and then gets processed around in our mind. We know our mind has all kinds of intuitions and predilections and predispositions that we never know at any given moment, whether we're insane, whether we're dreaming, whether we're delusional, whether we're drunk, whether we're being hopeful and emotional, whether we're biased, blah, blah, blah. What we have is data from the external world and a method for saying, if you don't believe what conclusions I've come to, here, you get the data yourself. Here, get tons and tons of data. Here, do the experiment again. Here, pass that experimental recipe on to your sister, onto your aunt, whatever. And what we're saying is, as scientists, is that from here on in, what the altar at which we worship is physical data being collected through reproducible, controlled, experimental designs. And what Newton is saying here is the data seems to say F equals GMM over R squared. It totally goes against my intuition. It totally goes against my comprehension. It totally goes against my hopes and my most basic sense of the world. But I'm a scientist. I'm here to tell you what I'm observing and measuring, and I'm here to report that. And I'm not here to bias my report. I'm not here to report what I want. I'm here to report what I seem to see. And what I seem to see, or what the data seems to suggest and then mathematically point to, is GMM over R squared. I don't get it, but I'm just a messenger. The message is driving me crazy, but here's the message. And thus I am a scientist, not a philosopher, not a theist, not a dreamer, not an emotional, of course I'm all those other things in other parts of my life, presumably I knew. But when I give you a scientific finding, I'm giving you a scientific finding, and it's not my business to like it or dislike it. That's how much of a scientist I am. Approval is no prerequisite for acceptance. That is science, right? I mean, this is what so again, if you have already heard the story, I kind of apologize that you had to hear it twice. On the other hand, it's one of my favorite stories in all of science, because it is the essence of scientific thinking, is reporting the science even when you don't get it at all. And Newton didn't get it at all. He got it enough to really not get it and for it to drive him crazy. Now, so and by the way, I'm so glad Walter shared. I mean, it makes me so happy that Walter shares that. Oh, sorry. I'm gonna look. But I mean, I got that story from my mentors, and it's also a story about how someone relates to their mentor and all of that. Like, Newton's literally using his intellectual mentor as a therapist in this letter, if you see what I mean. And the number of times that Walters and I have discussed this, I'm so thrilled that he passes it on as well and jumps my gun. And Walters was a student of mine, if that's not obvious, or whatever. But now, I mean, now I don't know who the student is and who the teacher is, but let me just look away. Okay, now, like what Sam's saying in the chat. I mean, look, yeah, I mean, and you give me a whole nother semester to, right? Of course, I mean, of course, all this stuff points to the deeper questions of what's really going on in the universe. I mean, I'm not even going to use the 3-letter word because it's like a dangerous word to some people, but yeah, and don't think, I mean, well, anyway, right. All I can say is right, and LOL spelled backwards is LOL. So there you go. So what does this do for us in the course, though? Like, where do we go with this? Like, because also I would be doing, I know there's 9 minutes left. So of course I'd be doing you a tremendous disservice, all of you, if I just said, and so the conclusion is science is crazy. And like, if you really do science, you're going to go crazy. And you don't even, if you really do science right, you're not even going to like science. So there you go. Goodbye. Like, no, that's not my point. My point is that if we believe things can pull on each other through empty space, then we believe that information somehow gets from one object to another through space. And that is such a hard idea to accept that we do invent a word for that concept. The word isn't God, the word is field. What we come to believe post-Newton, the way we construct our understanding of the world is, and this is where the equations on this sheet now come in, what we start to say, because it makes it easier for us to grasp this and makes it easier for us to do the math and easier for us to make predictions, is what we say is, okay, the sun does not just send its information out through empty space to Earth. It doesn't just, because that leaves too many unanswered questions. What we say from now on is the sun does not pull on the Earth through empty space with an immaterial force. What we say from now on is the sun creates what's called a gravitational field. And if the Earth finds itself somewhere in that field, the field pulls on the Earth. Similarly, we don't say that the proton pulls on the electron anymore in sort of modern physics. We say that the proton creates an electrostatic field. And if an electron finds itself anywhere in that field, it gets pulled by the field. Does this make, like, what's the difference? In other words, we introduce an agent, like a medium, like the medium for waves that we've been discussing. We now, because it's just too impossible for us, for our brains to handle the idea that raw information could get from the sun, transmitted from the sun to the Earth without anything in between containing or holding or propagating or sending that information. We say that what's in between the sun and the Earth, conveying and transmitting and holding that information, is something called a field. Mathematically, the notion of a field is actually, thankfully, quite straightforward. And this is finally now where the equations on the board come into play. If you look at the top equation, you'll notice it looks like what we've been saying last week. It looks like that, F equals GMM over R squared, and then times it. And don't worry about the R hat thing for. Here we actually. I'll go to the next page. Well, yeah. The gravitational field is mathematically, informationally, numerically, everything that the gravitational force is divided by one of the masses. In other words, the gravitational field, the gravitational field, lowercase g, is the force divided by one of the masses, specifically the smaller mass. The gravitational field is all of those numbers in the force expression, but divided by the second mass in the force expression. In other words, mathematically, a force is a number of newtons that one mass exerts on another mass. A force is an interaction between two masses. A field is all the information generated by just one of the masses. A field is force per mass. A field is not the gravitational field exerted by the sun is the number of newtons of force that the sun would exert gravitationally per every 1 kilogram of mass that could be at any given location nearby the sun. Force is measured in newtons, field is measured in newtons per kilogram, if we're talking about gravitational field. If we're talking about electrostatic field, electrostatic force is measured in newtons, electrostatic field is measured in newtons per coulomb of charge, right? So the idea here is, if you take the sun, and you take its mass, and you pick any location that you want, like some distance, 93 million miles, or 93 million miles from the sun. So you take the sun's mass and you take some location measured in meters that you're looking at from the sun, and you square that location, you square that distance. So you divide the sun's mass by that distance squared, and you multiply that whole package by the big G number, 6.67 times 10 to the negative 11. So you just take all those numbers together, all of that, and you don't put in any second mass at all. You just multiply that whole package by, in other words, by the number 1. You just ask yourself, how many newtons of force would the sun exert if there were 1 kilogram of mass just sitting there at that location? Then that's the amount of the sun's gravitational field at that location. And it's like a force waiting to happen. If you want to know the exact force gravitationally that would be exerted on the Earth, then you plunk the Earth in there and you multiply by its mass. In other words, the field is the total number of newtons being exerted on every single kilogram of the Earth. The field is the force per mass waiting to happen. And so field is force per mass. And if you want to calculate what force is, you multiply the mass back in. Force is field times mass. I know we've got 1 minute left. This in itself is just a mathematical construction. This doesn't solve all the epistemological problems necessarily that we were saying before, but you'll see that it starts to address some of them. What we say from now on is that the sun has this information about itself. It has its mass, it has its location, and it's plunking that information everywhere in the universe. It's plunking, like at every distance from the universe is a little bit of information describing the sun's mass and how far away the sun is. There's a little arrow, in fact, metaphorically, there's a little vector arrow that's pointing towards the sun. And a little bit farther away from that vector arrow is another arrow that's a little bit smaller, pointing towards the sun, a little bit smaller, because if we're farther away, the force would be a little bit weaker. And everywhere in the universe, there's a little bit of field from the sun, which is, what is that field? It's the information of how many newtons of force will be experienced by any kilogram that might be put at that location. And once a kilogram of test mass is put at that location, then it experiences the full force and starts accelerating towards the sun. So the sun creates a field, the field exerts a force on other objects, and all the information, the adjustments, the new updates information get propagated through that field, just like waves through a medium. Again, I'm not saying that I've answered all the questions of how this all works, but I'm saying that from now on, action at a distance we don't think of as happening through empty space. We think of it as happening through a field. The field is created by one object, and a force is then experienced by two objects. That's all for today. Thank you for listening so much. Obviously, there's no new homework or anything like that. I will see you in, I will. Oh, have a very happy Thanksgiving. I'll see you next week. Have a very happy Thanksgiving. Thank you. Thank you. Turn off. Happy Thanksgiving, indeed.